Hi everyone, we are here at the University of Illinois and we are talking with Professor Paul Kwiat, who is a professor here in the physics department, and this is us playing 10 questions or 20 questions about quantum computing. Thank you, Paul, for talking with us.
You're welcome.
Please introduce yourself for our audience.
So yes, I'm Paul Kwiat. I'm in the physics and also zero-time apportment and electrical engineering department here. I've been here since 2013, and my area of specialty is quantum information, experimental quantum information, mostly with optics, with photons, and a lot of things with quantum communication and a little bit with quantum computation. But I teach a quantum information course here, so I guess I'm hopefully qualified to at least tell you what other people know about this topic.
And you've been here since 2003, right?
2001.
2001, right. So you work in quantum computing, obviously, and I'm wondering if you can tell us what the differences are between quantum computing and the traditional computing that have been around for many decades.
Yeah, so I guess I'd say that there are two sort of main differences one could think about. So first of all, the classical computing is based on bits, things that can be zeros or ones, and I happen to have brought here an example of something that could be a nice bit, something that could be a 0 or a 1. Obviously, in a normal computer, it might be some voltage on some capacitor plate or something like that. And of course, all classical computers are equivalent in the sense that you can run any program on any classical computer. So quantum computing is quite different because in addition to having 0 and 1, this is just being an analogy, but in a quantum bit, a qubit, we can have something that's a 0 and a 1 at the same time, a superposition of 0 and 1. Okay, we'll come back to that in a minute because that's a problem. So that's one very different thing. And so there's a lot more information in a quantum bit than in a classical bit. You can think of, sorry, I don't have too many of these props, but there, we can write a general quantum state as a combination of a 0 and a 1, and it can have arbitrary complex coefficients as long as the sum of the squares of these two coefficients is equal to 1. And so you can think of that as being represented on because I have two coefficients here, and because the sum of the squares is equal to 1, that corresponds to two parameters, basically. So you can think of a quantum bit as represented like a longitude and a latitude somewhere on a sphere. So if you're at the top of a sphere, for example, you could call that a 0, and if you're at the bottom, you could call that a 1, and you can have 0 plus 1 or 0 minus 1 or 0 plus I1, basically anywhere on the surface of the sphere. So that's a lot of information compared to classical. So that's the one sort of part difference. The next thing has to do with gates. So of course you have gates in classical computing, and you also have them in quantum computing. If you think about a classical computer, for a single bit, there's only one gate. Well, I guess there's two. There's the identity. You computer scientists probably call that a gate, but anyway, that's not a useful one. And then there's the NOT gate. So in a quantum computer, all gates on a qubit become rotations about some axis on this sphere. So for example, we might rotate about this axis, this horizontal one, and that would take 0 to 1 and 1 back to 0. And every state on the sphere would get moved, well, except for the two that at the axis. So basically, it's a much more complicated set of gates that you can have. And also, if you combine different gates together, qubits together, where we have two qubit gates or something like that, then you can generate much more interesting states, so-called entangled states. And so just as an example of that, if you had a classical computer that had 3 registers, we'll do 3 registers. With 3 registers in a classical computer, you would have one of 8 numbers, because you could have 0, 0, 0, or 0, 0, 1, or 0, 1, 0, or 0, 1, 1. Okay, 2 times 2 times 2, one of 8 numbers. But in the quantum case, you actually get, if I can do this, you actually get all 8 numbers simultaneously in the computer at the same time. Okay, again, ignore the fact that these are decohering, that these are dropping out of that for the moment. So with just 3 registers, that's not so impressive. But if instead you had 300 registers, which your iPad or something has millions of registers in it. But with just 300 quantum registers, you can encode up to simultaneously 2 to the 300 numbers. And 2 to the 300 is like 10 to the 100 or something like that. And that's more than the number of particles in the universe. So even if you were to count every electron, you run out of particles before you get the number of states you could simultaneously put into a quantum register. And so that's going to enable a tremendous speed up in solving certain types of problems. And in particular, I guess the funny way of putting it is that there's an exponential speed up on an exponentially small number of problems, because it's not good for everything, but for some things it definitely has a huge benefit.
So essentially, when we do parallel computing, say with 4 processors, it might get sped up 4 times. It might be 4 times faster. But essentially, what you're saying is that with a quantum computer, you could be as fast as you possibly can, because essentially you have an exponential speed up.
Yeah, it would be, well, it would be like 2 to the 4 times faster.
2 to the 4 times, right. So we hear this term called qubits in quantum computing. Can you say what it is?
Well, a qubit is just the term of a quantum bit, so any representation of this 2-level system, so bit, but that can be in superpositions of the 2 at once. And so maybe I'll just talk about how you might get that physically in a physical thing. Yeah. So the simplest example maybe is, I guess there are sort of 2 that are pretty easy. One is, from chemistry, you know that in atoms there are electrons, and electrons have these different orbitals. And so, for example, you could call, if the electron is in its lowest orbital, you could call that a 0. If it's in some excited orbital, you could call that a 1. And you can put the electron so that it's in a superposition of 0 and 1 at the same time. It's in a superposition of both these locations at the same time. If that seems really impossible or weird to you, I would say, yes, true. But already the fact that when it was in the 0 state, the electron was already in all these different locations around the nucleus at once anyway. So in some sense, it's not really any, we've already had the weirdness put in. And now the question is, can we use that to do something? That's one possible way of getting of encoding a qubit. Other things that people have looked at is in superconducting coils, you can have the current going clockwise being a 0 and counterclockwise being a 1, and then you can get the current of electrons to be both going clockwise and counterclockwise simultaneously. I deal with optics a lot, and so we can use properties of photons. The one that we often use is the polarization of the photon, whether that's horizontally or vertically polarized, just like you would get with 3D glasses in a movie theater. And you can make superpositions of, say, horizontal and vertical, and that would give, say, something that was diagonal. And so it's real easy to see how you get those superpositions. Or if there are superpositions with a 90-degree phase shift, then you get circularly polarized light. And that's how not the IMAX 3D glasses, but the other one, the real 3D or whatever, they use circular polarization. So it's basically, the qubit is basically any quantum system that can be mapped onto a 2-dimensional space where you can make these superpositions of the properties in that space.
And what kind of problems is quantum computing used to solve nowadays?
They were originally proposed by Richard Feynman as a way of basically solving physics problems, of doing simulation. So just like any classical computer can run any classical architecture program, any quantum computer in principle can solve any quantum mechanics problem, but in a way that's maybe a lot more controlled than you would normally have with the actual system that you're trying to study. So certainly quantum simulation is something that people look at a lot as a possible application, and I'll come back to that in a little bit. The main one that really started the whole field, though, is so-called Shor's algorithm. So Peter Shor, the theorist, I think at IBM at the time, who figured out that you could factor large numbers into their prime constituents using a quantum computer, and it wouldn't require the exponential speed up that we currently have. So currently with classical algorithms, it's an exponentially, as you increase the number of digits, then the time to do the factoring increases exponentially. And with a quantum computer, it doesn't, it decreases, it's only polynomially. And so there's a huge interest in that because, of course, of that difficulty of that problem, or the perceived difficulty, is what a lot of our current classical encryption is based on. Like RSA encryption is based on the fact that that should be a hard problem to solve. It's not mathematically proven that it's hard that's a so-called NP-complete problem, or that it's a difficult problem, but it's strongly believed to be. So at the moment, what's driving this is this factoring sort of thing in terms of quantum computing, and then this possibility of doing quantum simulation.
You mentioned quantum computing being used to potentially break RSA cryptography. Is it possible to use quantum computing to come up with new ways of encrypting and decrypting data?
There are 2 answers to that. The answer is yes in both cases. So first of all, people try to find algorithms, classical algorithms, that are not susceptible to this exponential speed up. And so if you use, I think it's elliptic curve cryptography, I think I don't know, you're the computer science person, and maybe also Diffie-Hellman in coding. Those you only get a square root of n speed up because it's like this search algorithm basically, so that's not such a big speed up. So one thing is to try and redo your classical cryptography in ways that are not so susceptible to quantum computers. The other thing that you can do is quantum cryptography, which is actually mostly what my group is involved with, not so much quantum computing. And that's basically using single photons to generate a random key that you can then use to encrypt information. And because you have a single quantum system, and it's very fragile if you make measurements on it, so it's very fragile in the sense that this thing doesn't like to stay spinning in that sense. You can encode information in a way that you can detect if there's an eavesdropper who's been trying to monitor that information. And then you simply never have any transmissions that are encrypted using a key that an eavesdropper could have looked at without you knowing that an eavesdropper looked. So either you know that no eavesdropper looked at it, in which case it's secure and you can use it, or maybe you know that an eavesdropper did look at it, and then you just never use that key to encrypt anything. So in that sense, it gives you perfectly secure encryption. That is not breakable by a quantum computer, because basically it's just using so-called one-time pad encryption, where you just have your message and you add to each bit of the message, you have your key, which is a random string of zeros and ones, and to each bit of the message you just add a bit of the key, modulo 2. This is a string of zeros and ones that you want to send. This is a random string of zeros and ones. When you add these random string to this string, you get a completely random string. You just post that on the internet, or you call up the person, or you put it on Facebook or whatever. And if the recipient knows the same key, then they can undo the process and they get the original thing. Because what's being transmitted over the internet is just a random string of numbers, there's nothing to be broken. There's no code. There's no structure in it at all. It's just a random string of numbers. So it's never going to be possible to do some sort of processing on that to figure out what the original thing was. Now, if you don't do the implementation, so the whole quantum cryptography is all about distributing this key between the two players. And if you don't do that right, if there are what will I say, loopholes in your experimental setup, then you can hack that kind of a system. And that's also been done in the last couple of years, where people have started hacking quantum cryptography systems and finding out, okay, there's a big difference between theoretically drawing the protocol and then how you actually implement it. And are you leaking extra information when you're implementing it?
So in all of this, it seems like there's a lot of ideas in quantum computing and quantum cryptography. How far are we from seeing a truly powerful quantum computer, one that is, say, similar to one of our data centers, or maybe even weaker than that?
In terms of that, how long is it till we have like a universal quantum computer or something like that, or one that could factor some very large number? Yeah, there's a physicist, Bill Phillips, who got the Nobel Prize a number of years ago, used to say that it's a 50-50 proposition with quantum computers. There's a 50% chance that in 50 years we'll have one. So let me just put that in perspective. We now have 14 or 15 qubits. That's the world record. And I might say a little bit about this other company, D-Wave, that's been in the news a lot. For universally accepted and recognized quantum computing efforts, the record is about 15, with maybe hundreds of gate operations, something like that. If you want to do quantum simulation, you need to have of order 30 or 40. And so 30 or 40, we're going to have that in 5 years or 10 years. I don't have any doubt about that. Whether or not we can get to this large number of gates that we need to do a useful simulation, that's a different question. And in order to do quantum factoring, then as I say, you need 50,000 or something like that. So there are people working on a lot of different efforts, a lot of different systems using ions or superconducting qubits or photons or something like that. The main difficulty, if I can just go back to my example here, the main difficulty, assuming this doesn't fall off the table, is that doesn't like to stay in a quantum superposition. It interacts with the environment. In this case, it's interacting with the air in the room and also with friction on the table, and that's causing it to collapse into being into either a 0 or a 1, not the superposition of 0 and 1. This is obviously just an analogy, but this happens with every quantum system, that it doesn't like to stay in this quantum superposition because it's interacting with the environment. And so you might say, well, okay, that's fine. I could put this in some evacuated chamber so it's not interacting with the environment and somehow magnetically levitate it or something like that. That's true, you could, but there's another thing you need for qubits to do, they have to be able to talk to each other. You need to do these gates. So in this analogy, it would be that the spinning of this one impacts how this one spins, which actually it does a little bit, but we need to interact on a really strong level. So they have to interact really strongly with each other and not with the environment. So then you say, okay, well, that's fine. I just take these, I put them up in space somewhere. They're completely isolated, and they just interact with each other, and that's fine, except for the fact that there's two more things you need for any computer at all, and that's you have to have input and output. So you've got to be able to input into your computer what's the number you're trying to factor, for example, or what's the molecule you're somehow trying to simulate. And then at the end of the day, you need to make this readout of a single quantum system out. And here, it's really easy because I just slap my hand down and I see this. But if you're actually trying to read out what the state of a single electron is, a single photon is, something like that, that tends to be a lot more. You need to have strong interactions to do that. So basically, we need to have very strong interactions with the qubits to put the information in. We need to have no interactions with them while they're doing their dance and running the algorithm. And then at the end, we need to have very strong interactions again. And those are just hard. It's hard to do that. This interaction with the environment, that's known as decoherence. That's the technical term for that. And it happens with any physical system that we know about. So that factor of decoherence is a problem. So you need to do some sort of error correction in order to do any kind of a long algorithm. Just like in classical computing, of course you do error correction. The thing is that in classical computing, you can do things like best 2 out of 3 encoding. So you could just run this every step, say 3 times, and then you would just take, assuming that if they all 3 agree, you say that's the right answer. If 2 of them agree, you take the 2 and you say the 1 was an error. And then by doing that sort of concatenation of that, you can really get the errors small. The problem is that in a quantum computer, you're not allowed to measure what the results are in the middle because that stops the whole computation. So you have to do more complicated schemes of encoding. And it turns out you need to have of order, let's say 7. If you can have 7 physical qubits, then you can correct any single logical qubit error. So whether an error could be a flip error, so something a 0 becomes a 1, or it could be a what we call a phase error, which would be that this sort of gets rotated around. Or if you think about this longitude and latitude, a flip error would be doing this, and a phase error would be doing a rotation, an unwanted rotation like that. So if you can encode in 7 physical qubits, 1 logical qubit, then you can, it turns out there are ways of then measuring them in a way that doesn't kill the quantum computation, and you can correct those errors, and then you can continue.
It's pretty fascinating. If one of our audience members is interested in knowing more about quantum computing, is there a good book or a reference that you might suggest?
If you just Google quantum computing, I mean, there's lots of Wikipedia articles, lots of tutorials on it. I mean, quantum computing tutorial, and there's tons and tons of web pages on it, about it. I actually wanted to say one more thing about an algorithm thing that is relatively new that might be of interest. So there's a problem called the boson sampling problem, which is equivalent to finding the permanent of a matrix. Computer scientists supposedly know what this is. I didn't know what it was, but the permanent is like the determinant of a matrix, but you make all the minus signs plus signs. And it turns out that finding the determinant of an n by n matrix is something that's exponentially hard. And it's now known, it's now believed anyway, that if you take that you can map that problem onto a very physical problem, and the physical problem is you've got a bunch of photons, which are particles of light, and they come into a network that has a bunch of beam splitters that connects things. So the beam splitters are just like this piece of plastic that I had, where the light sometimes goes through and sometimes is reflected, and you make this complicated web, and it's got maybe n inputs and n outputs. And the question is, for given inputs in here, and for given basically, depending on what the reflectivities and transmissivities of each of the elements in this network are, what's the distribution of where the things are going to show up? So what's the probability distribution? And that is mappable onto this permanent problem, which is known to be exponentially hard. And yet the quantum case seems to just solve it. You just send the things in, and you see where the photons show up, and it solves it. And the reason that's relevant is supposedly then that would violate the extended Church-Turing thesis, because you'd be able, with this system, you'd have a system that would be able to solve an exponentially hard problem. And so that is something that's of great interest at the moment, both from a theoretical point of view, and also that requires of order maybe 30 photons or something like that, or 40 photons. And so I guess in the next 5 or 10 years, that will also be done. And I don't know, either the quantum mechanics will somehow break down, which would be impossible, or the Church-Turing Turing thesis would break down, which I think the computer scientists would also say is impossible. So something's going to fall, and that's kind of interesting.
So I wanted to wrap up with a question that's changing gears a little bit, not related to your technical work, but you've worked in the university for over a decade now. Before that, you were in a national lab.
Los Alamos National Laboratory.
Right. So I wanted to ask about, how do you think, what is the difference between working in these two different environments?
So one thing is there's more bureaucracy at a national lab. There's no question about that. And we have colleagues who come to us from NIST, National Institute of Standards and Technology, and they have extra travel restrictions and computer restrictions, and they have to change their passwords every 2 months. I was at a talk once where someone couldn't remember the password to his computer, and that was really kind of annoying. So that's one thing. There's quite a bit more bureaucracy. Of course, you're not teaching at a national lab, and that can be a positive or a benefit, of course, depending on how much you like teaching. I happen to like teaching, so for me, it's much better being here. The scale of resources at a national lab tends to be bigger in the sense that if you're at Sandia National Lab, they have fabrication facilities that make our facilities look not good. And we have some of the best facilities that you can find at any university anywhere, and yet the Sandia ones completely blow us out of the water. And so if you need to make, you need a class 10 clean room or something like that, they have such things, and they can do all kind of fabrication. On the other hand, things are a lot more expensive at a national lab, and a lot of times you have to get funding to work on whatever project you're doing. Same thing here, but also as professors, we're paid to teach during the semester, during the years, I should say, and that covers a lot of our salary, whereas if you're really working at a national lab, you have to find some sponsor who's, unless you're working on whatever, it kind of depends what kind of project you're working on at the national lab. But certainly places like NIST, really fabulous. I would love to work at a place like NIST. I wouldn't really love it more than working here, but I certainly wouldn't mind recommending people to go to some place like that or Sandia National Lab. It's really a good experience. The one thing I miss is that here you get a lot of unanticipated questions because you have students who don't know whatever. They don't know anything, and they come and ask questions, and by and large, almost none of the questions are ever stupid. But some of them are really incredibly insightful and cause you to think about things that you'd never think about on your own because we have a certain perspective and we sort of have this certain set of knowledge, and all of our questions are somehow related to that sphere of knowledge. And then the kid who doesn't know any of this comes in and he has a question that's out here, and that really forces you to sort of think outside that. And I find that very, it certainly can certainly be refreshing. And also, I love working with students. I mean, they're very bright, and that's a great thing. Sometimes national labs have them, sometimes they don't. It really depends. But it's certainly an opportunity that's worth looking into.
So your advice to students would be don't stop asking questions, even if you think they're stupid questions.
I've very rarely seen stupid questions, unless there's procedural things about, is the homework really due, blah, 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 or something like that. But in terms of science things, people, the questions might just reveal that we haven't really quite given enough information in lecture, and so, people are trying to make some logic jump and they don't quite have all the pieces, or they misunderstood something. I mean, all of these topics, whether it's quantum physics or high-end, computer science, they're not easy topics. And so everyone's trying to put this scaffold of knowledge together in their head, and sometimes it doesn't, it doesn't quite fit. And a question can really cause it to fit, or it can reveal that, oh, there's this whole other avenue that can be looked at. So,
okay, thank you for talking with us, Paul.
You're welcome. My
Thanks.
pleasure.
Professor Paul Kwiat.